space. Okay, so let's start with an example. So what is this example? I'm going to take set of all n cross n matrices. Okay, so this is how I'm going to write. It is all those A such that this A belongs to Rn cross n. Okay, it's basically set of all n cross n matrices. Will it form a vector space? Yes, right? You agree? We saw that in the, I think, in one of the classes earlier. The set of all 2 cross 2 matrices formed a vector space. So this forms a vector space, right? So this is a vector space over what? R, right? R is the field. Okay. Now I have to, well, I can think of these matrices as vectors. How do I think of these matrices as vectors? I can stack one column below the other and get a very big vector of dimension n squared by 1, and therefore that's a vector, right? So I can still think of it as a vector. But let's restrict ourselves to the set of all matrices. Let's not stack it, but it turns out that it's equivalent to that. So now how do you define the inner product here? So this is a vector space. Now, is it possible to define some sort of a dot product kind of thing here, which is called inner product? So how do you define inner product? You take two matrices A, B. What is the inner product? Yes? I cannot say A, B, right? A times B. Because it gives me a matrix. I should get a number. So how do you get a number from a matrix? Huh? What are the possible things that you can do? Huh? Sorry? Transpose? You are saying A transpose B? Huh? Well, this is still an n cross n matrix, right? It's not a number. So how do you convert this into a number? Huh? Okay, so let's look at determinant. I haven't even spoken about determinant yet, right? So if you have determinant of A, B, right, it gives me a number, fine. But is it linear in A and linear in B? That's also we need, right? Is determinant linear? Well, not really, right? It's highly non-linear, because if you look at determinant of A, that's a polynomial in the entries of matrix A, right? You'll have A power n and A11 power something and so on, right? So it's highly non-linear. So I cannot use determinant. What else I can use? Huh? Trace, right? So that's something that sum the diagonal. Take the product of two matrices, sum the diagonal. That's all, right? So it's linear in A. It's very clear, right? Trace of A plus B is trace of A plus trace of B. Very simple, right? So sum of the diagonals of the sum is the sum of the diagonals, right? So, okay, is this clear? This is definitely a inner product. Why is that? For example, if I look at A, what do you get? Trace of, well, I get A squared. What is the issue here? Is trace of A squared always positive? Huh? But I have to ensure that this in A inner product with A is always non-negative, right? But if it is negative, then this is not the right way to define inner product, right? So how do you ensure that? Essentially what I have to do is have to ensure that the sum of the diagonals is positive, right? Non-negative. Or if I can ensure that the diagonal entries are also, all the diagonal entries are non-negative, that's also fine, right? How do you ensure the diagonal entries to be non-negative when you look at A inner product with A? There's one way, right? So I'll put a transpose here. So what do I get here? A transpose A. Okay, what do you get in the first 1, 1 entry? What do you get? So what is the first entry in the diagonal if I look at A transpose A? So let's look at that. Let's write the picture. So you have this big matrix. This is the first, let's look at the first column of this. This is A, right? This first column, right? Now what is A transpose? that goes here, right? A transpose, if you look at the first row, that's nothing but the first column of A, right? So this and this are both same, right? If that's like you take a vector and take the transpose and multiply with the vector A transpose A. What is A transpose A? Positive, right? Non-negative. What about the second? Second row here is the second column of A, right? So that corresponds to this. Now when I multiply this with this, I get another positive number. This is 2, 2 entry, right? And so on. So all the diagonal entries will be non-negative. Okay. So this will be greater than or equal to 0. When will it be equal to 0? Well, all the diagonal entries should be equal to 0. When will all the diagonal entries be equal to 0? When A transpose or AI transpose AI is 0, right? When will that happen? AI is 0. That means it should be AI should be 0 for every I. That means the entire matrix should be 0, right? Well, it's consistent with our definition. Okay. So now that means I have a good inner product. So now I have to basically take that inner product and use it to get the norm, right? So what is the norm, induced norm here? What is the induced norm? This is square root of trace of A transpose A, right? What is this, by the way? If you look at trace of A transpose A, what do I get? I'm taking the first row, first column, multiply with itself, second column, multiply with itself, and so on, and then adding them. If you look at first row, multiply with first row, what do you get? First entry square plus second entry square, and so on. The second row, what happens here? It's the entry, all these entries squared, right? And you are adding them, right? You are taking trace, by the way. So in other words, this trace of A transpose A is nothing but you square every entry of the matrix A and add them, right? That's what it turns out to be. And if I take square root, that gives me a norm, right? What is that norm called? There is a name for it. It's called Frobenius norm. Is that okay? Fine. So this is how you get Frobenius norm. Well, you might ask a very important question. Can we come up with other norms? The answer is yes. You can come up with other norms here. Okay. There are uncountably many norms that you can come up with. Right? We will see how to do that, but soon. But keep that in mind. This is not the only norm. This is an easy norm to deal with and most famous norm. Right? Okay, you have a Frobenius norm for matrices. Okay, fine. Okay, so let's move on now. So let's look at a few other geometry of these vectors. So we have the notion of inner product, we have the notion of norm, right? So what else we need? So eventually I want to solve some set of algebraic equation, right? Like Ax equal to B kind of thing. And we also saw that if A is diagonalizable things, or if A is diagonal, things are good, right? It's easy to find the solution. So now an important question is, when can I simplify this matrix A, right? So in order to do that, let's look at a specific in order to achieve that, the first decomposition that we are going to study, we need something called we studied basis, right? What are bases? Linearly independent vectors that span the entire space, right? But I can have a nice set of bases called orthogonal bases, right? What do you mean by that?